Hey guys, this is the lecture number 2 of limits, and in this particular lecture we'll solve some of the problems of limit, and we will discuss about the left hand limit and some of the algebra of limits also, right? So this lecture will be the very important for academic purpose and also for any other competitive exams, right? So let's start the video by showing you the first slides of today's lecture, which is actually the left hand limit, right? Here some spelling mistakes happened. You have to correct it, and that should be actually, that should be left hand limit, right? There is some difference, right? Okay, so what is left hand limit, right? We say that left hand limit of fx, I mean the given function as x tends to a exists and is equal to L2. I mean if the given function, actually here you can see we have already discussed about what is right hand limit, right? What is right hand limit, right? We have already discussed about it. Right hand limit is basically looking like that, right? Limit extending to a plus and the given function is fx, right? Suppose a function which is fx is given to you and the limiting approachable value is extending to a plus. So we have to take the value of a on the right side, right? Which is the nearest value of a. Similarly, for the left hand limit, we have to take those values which are left side on A and also contained in neighborhood of A. So actually the definition says, we say that left hand limit of fx as x tends to A exists and equal to L2 if as x approaches to A through values less than A. So if we have to approach the value of x which is less than A, then the values of fx which approach a definite unique real number L2, right? So as x approaches to A minus, I mean the very lesser amount of, it is very close to A but not equals to A, and also it is less than A, then the given function fx approaches to a particular real number which is L2. Then this is called actually the left hand limit of fx at x equals to a, and it is written as limit x tends to a minus fx which is equals to L2. I mean as x approaches to a minus, as x approaches to a minus, the given function which is fx approaches to the value L2, right? So this is actually the definition of left hand limit. So you can understand what is the definition of left hand limit. Let's move to the working rule of left hand limit, right? So we have to move to the working rule. We have to move to the working rule of left hand limit. I'm just write down as LHL, so you can understand LHL means left hand limit, right? So in order to evaluate the left hand limit, which is here the general term is limit x tends to a minus fx, right? So this is the general term. We have to do two steps, right? One is put x equals to a minus, right? And in fx, to get limit h tends to 0 f of a minus h, and second step is take the limit as h tends to 0, right? So basically we are discussing about two types of limit. One is right hand limit RHL and one is left hand limit, right? So how we can actually do some working rule for right hand limit? It is actually looking like, I'm just writing down here as limit x tends to a plus fx, right? I'm just taking the function as fx, and the limiting part is actually a plus. Similarly, for the left hand limit, it would look like limit x tends to a minus fx, right? Right? These are the two basic limits. So when you will see that this type of limit, it is actually the right hand limit of fx at x equals to a, or you can say at x tending to a plus, and this is the left hand limit of fx when x tending to a minus, right? So the working rule basically is, so the working rule of right hand limit is basically we have to put x equals to a plus h. We have to put x equals to a plus h, and we have to take the limit as h tends to 0. I mean limit h tending to 0, limit h tending to 0, f of a plus h, right? This is the basic form, basic formula, right? This is the basic formula for the right hand limit, right? Similarly, for the left hand limit, what we have to do? So what are the working rule? It is actually showing in this particular slide, but I'm right down here. We have to take the value x equals to a minus h. You can see the difference, right? In the right hand limit, we have to take a plus h, and in the left hand limit, we have to take x equals to a minus h. And then we have to take the limit as h tends to 0, h tends to 0, f of a minus h, right? A means nothing but x tending to the particular value. Suppose if x tending to 2, then we have to take x equals to 2 minus h for the left hand limit, and for the right hand limit we have to take x equals to 2 plus h, right? H actually tending to 0, I mean h is not equals to 0 but slightly higher than h or something, then definitely 2 plus h is actually greater than 2. That is why we have to take the right hand limit as 2 plus h, and for the left hand limit we have to take 2 minus h, right? So you can understand. So in order to find out the left hand limit of a function fx when x tending to a minus, we have to take x equals to a minus h, and then we have to take the limit as limit h tends to 0, f of a minus h, right? So let's move to some examples so that you can easily understand how actually we have to find out the left hand limit. So basically, in order to find out the left hand limit, first of all check whether the equation or the question is given to you is actually a left hand limit or not, right? I mean, here you have to see, right, whether x tending to 3 minus or 3 plus or 3 is given to you. Here you can see you have x tending to 3 minus. So this is actually a left hand limit problem, right? It is actually left hand limit problem. So there is no issue, right? So we have to take let x equals to a minus h, and here a means 3, so we have to take x equals to 3 minus h, right? So that function will become limit h tending to 0, limit h tending to 0. Then instead of function, here the function is x cube, so we have to put x equals to 3 minus h. Then the function will become 3 minus h whole cube, right? So it will become limit h tending to 0, h tending to 0, that will become 3 cube, which is 3 cube minus 3 times 3 square into h, right? Plus 3 times h square and minus of h cube, right? I'm just applying the formula which is a minus b whole cube, which will be a cube minus 3a square b plus 3ab square minus b cube, right? So it will become limit h tending to 0, 3 cube will be 27 minus 3 times 3 square will be 3 cube again, so it will be 27h, it will be 3 times 3 which is 9h square, and it will be h cube, right? So that part we can substitute the value, right? We can substitute the value here. So we have to apply the substitution method. Because when you substitute the method, substitute the value of h as 0, then it will not it will not give you the form of 0 by 0 or infinite by infinite or 0 to the power infinite. I mean, the indeterminate form you will not get. So we can do this, the substitution method. It will be 27 minus 27 minus 0 will be 0, right? 9 times 0 square will be 0, and 0 cube will be 0, because h is actually, we have to put h as 0, right? So it will become 27. So you can see that the left hand limit of x cube when x tending to 3 minus, the value will become 27. So let's do again. Let me change this 3 as 1 minus. Let me change it. This will also work, but 3 minus and 3 minus both are same, that is why I'm just changing, right? So you can see that this is also a left hand limit question. So in order to solve a left hand limit question, first of all you have to do x equals to, I mean the given variable equals to the tending value, which is actually 1. So 1 minus h, right? For the case of right hand limit, we have to take 1 plus h. For the case of left hand limit, we have to take 1 minus h, right? So that will become limit h tending to 0, x square will become 1 minus h whole square plus 3 upon 1 minus h plus 2, right? So that will become limit h tending to 0, 1 minus h whole square will become 1 minus 2h plus h square plus 3, and the denominator will become 1 minus h plus 2. I mean 3 minus h, right? So let's substitute the value, because when we substitute the value, it will not form a undeterminate form, right? So that will be 1 minus 0 plus 3 upon 3 minus 0. We have to just substitute h as 0. So that will become 1 plus 3, which is 4, and the denominator will be 3. So the left hand limit of that particular function is equals to 4 by 3, right? The 4 by 3. Okay, so let's take a slide so that I will show you something very interesting, right? So what is actually, so left hand limit and right hand limit, right? So why you have to find out these two? In order to, suppose you have a given limit function which is actually limit x tending to a fx, and you have to find out the value of this, right? So why you need to find out the left hand limit and right hand limit, right? So before starting and before telling about these things, let me give you a very important thing, or a very realistic thing, which is, suppose this is your goal, this is your goal, right? And this is your brain, this is your brain, and this is your heart, right? This is your brain and this is your heart, right? So suppose your brain says that this goal is a perfect goal, and your heart says this goal is not a perfect goal. I mean, your brain says tick and your heart says wrong, I mean cross. Then do you see that the will you achieve that goal? I mean, when your brain says, yeah, this goal is perfect for you, and your heart says that this goal is not perfect for you, then what do you think, that will you achieve that goal? I feel like you will not achieve that goal, or however you will achieve that goal, then you will not satisfied, right? For your entire life after achieving this goal. But suppose your heart says that this goal is right for you, but your brain says this goal is not right for you. Then will you get succeed when you achieve that goal? Obviously not, right? So when you will succeed when you achieve that goal, when your brain says click, I mean tick, and your heart says tick. I mean, your brain says, yeah, that is your perfect goal, and your heart also says that that is your perfect goal, right? Then when you achieve that goal, you will be very succeed, you will be a successful person, right? Similarly, this particular limit value, when this particular limiting value will exist when left hand limit and right hand limit exist and those are equal. I mean, if limit left hand limit would look like limit extending to a minus fx, suppose that value is actually L2, right? And the right hand limit, which is limit extending to a plus fx, which value is actually L1. So that particular limit will exist when L1 equals to L2, right? That is very important. When left hand limit and right hand limit will exist and those are equal, then we can say that the limit of the core of the limit, which is actually limit extending to a fx, which exists and which is equals to L. Let's say L1 equals to L2 equals to L, then that limit will also L. I mean, if left hand limit, suppose left hand limit is 2 and right hand limit is actually 3, then you can see left hand limit and right hand limit exist, but they are unequal, they are not equal. Then definitely the limit, then the limit of the of the function will not exist. But if left hand limit is 2 and right hand limit is also 2, I mean both are exist and also they are equal, then the limit will exist. So you can understand that when left hand limit says yes and right hand limit says yes, and they both are says like this is the exact value and they both are satisfied with that particular exact value, then the limiting value of the exact function of the given function will exist, and that particular value will also L, right? So you can understand, right? So in order to exist a limit, that must be satisfied the left hand limit and the right hand limit, and those left hand limit and right hand limit should be equal. If left hand limit and right hand limit will not equal, however they exist, right? Then the actual limit will not exist, right? Okay, let's move to the next slide, which are actually algebra of limits, right? Algebra of limits. What is actually algebra of limits? In this particular lecture, we'll solve some of the algebras, which are like addition, subtraction, multiplication, division of functions with limits, right? So what says actually? If limit x tending to a fx equals to L. So here you can understand that limit x tending to a, limit suppose here you can say limit x tending to a fx equals to L is given to you, right? Limit x tending to a, limit x tending to a fx equals to L is given to you. I mean the function will tend to L as x tending to a, right? As extending to a. Similarly, limit extending to a, the function which is gx, which is equals to m. I mean the function gx will tend to m as x tends to a. So here you can say that the approachable value which are same actually a, and the functions are actually different. One is fx and another is gx, and the limiting values are actually L and M for the function f and g respectively, right? So you can understand that the left hand limit and the right hand limit of that particular particular limit will exist, and they both are L. That is why limiting value exists, right? Similarly, for the case of this particular function, the left hand limit and right hand limit exist, and these are also equals to m, right? These are the general thing which you can understand, right? Okay, so limit of fx is equals to L and limit of gx is equals to m. Then the following results are true, or you can say then the following results are hold, right? Which are the results? Hold, right? Which are the results? One is limit extending to a fx plus gx. I mean the sum of the given two functions, at limit extending to a is equals to limit extending to a fx plus limit extending to a gx, and we know limit extending to fx value is L and limit extending to a gx value is m. So basically what is actually trying to say, suppose you have a function limit x tending to suppose 2 and x squared, which is nothing but 4. Similarly, limit x tending to suppose 1 and you have 1 by x, which is equals to 1, definitely, right? We are just substituting the value. Then here you can see the given two functions are actually x squared and 1 by x, and x, sorry, you have to take 2, so the approachable value should be same, then it will become 1 upon 2, right? So then the question says that if we take the limit as extending to 2, when we summing the given functions which are actually x square plus 1 by x, this is actually similar to limit extending to 2 x square plus limit extending to 2 1 by x, and these are equals to 4 plus 1 upon 2. So when we get these types of value, we can actually break these two parts, right, in this format. and that will become 4 plus half, that will be actually 9 upon 2, right? So sum of two functions at limit extending to a is uh, equals to limit extending to a fx plus limit extending to a gx, which is equals to actually L plus m, right? L plus m. So similarly, if we just replace the positive plus sign with negative sign, which is fx minus gx, I mean, we have to subtract these two functions, which is fx and gx. So we have to do fx minus gx at limit extending to a, then that will become limit extending to a fx minus limit extending to a gx. So we know, right, limit extending to a fx will be L and the limit extending to a gx will be m. So that will become L minus m. So in general, if I write down, if I write down something, if I write down something like, suppose limit extending to a fx plus minus gx will become L plus minus m. So if I take positive sign, that will become L plus m. If I take negative sign, that will become L minus m. So you can understand what is the algebra of limits in these two particular cases, right? Let's move to another algebra of limits. So which are actually, and the third number of algebra of limits, which says is limit extending to a. So the first case is same, which is limit extending to a fx equals to L and limit extending to a gx equals to m. Then the following results are true. So let's copy that part and let's paste that one, right? So that part is always same, which is limit extending to a fx equals to L and limit extending to a gx equals to m. Then the following results are true. So the result is actually limit extending to a k, right? K times fx. So what you have actually, limit extending to a k times fx. So we are just multiplying the function with, we are just multiplying the function with a constant term, right? Constant term. So that will become k times, that will become k times limit extending to a fx. You can understand, right? This is actually the formula, and we know limit extending to fx is nothing but equals to L, right? Limit extending to fx is nothing but equals to L. So that will become, so that will become k times L, right? Let's take an example. Suppose limit extending to 2 to 5x square is given to you. Since 5 is a constant term and the given and the function is x square, so we can move this 5 outside of the limit. So that will become 5 times limit extending to 2 x square. So that will become 5 times 2 square, right? That will be 4. So 4 times 5 will become 20, right? So this is also very important. If a constant term is multiplied with a function, then we can actually take that constant part outside of the limit, and we can take the limit with only the pure function of x, right? Yeah. Let's move to the next slide. So similarly, that particular thing is actually holds, which are actually limit extending to fx equals to L and limit extending to a gx equals to m. So this is actually the general things, right? So you have to remember that thing. Okay. So what this particular 4 and 5 results says, which is actually the product. This is called the product rule, and this is called the division rule. What the product rule and division rule says is, if limit extending to a fx times gx is there, so if we have to calculate the product of the two functions, which are actually fx times gx, so then that will become limit of fx times limit of gx, right? That will become limit of fx, I mean limit extending to a at limit extending to a fx times limit extending to a gx. So you can understand, if the functions are multiplied, the limit can separate these two functions with multiplication. I mean, if limit extending to a, if we have to find out the limit of fx times gx when x tending to a, that will equals to limit extending to a fx, that will equals to limit extending to a fx, and times limit extending to a gx. And obviously, you know, limit extending to a fx is nothing but L, and limit extending to a gx is nothing but M. So that will become L times M, right? So you can understand, right? Suppose if I will give you an example, a basic example, which is suppose limit extending to 2 x squared times suppose e to the power x. So here this is a function and this is also another function, and they are actually multiplied with each other. So by this particular method or by this particular result, we can separate these two particular functions with limits. So that will become limit extending to 2x square times limit extending to 2 e to the power x. So that particular part will become 2 square, right? And that particular part will become e to the power 2. We're just substituting the value. So that will become 2 square will be 4 times e to the power 2. I mean 4e square, right? So that is actually the result says. Similarly, this is actually the division result, which is if we divide these two functions, I mean fx by gx, and if we take the limit when x tending to a, then that will become limit of fx when x tending to a, limit of fx when x tending to a, limit of fx when x tending to a, upon limit of gx when x tending to a, right? That is actually distributed, and that will become definitely L by M, because limit of fx is nothing but L and limit of gx is nothing but M when x approaches to a, provided M is not equals to 0. I mean that particular M should not be equals to 0. If that part M equals to 0, then that L by M will be undefined, and we can't find out, we can't find out any undeterminate form, right? Any value of undeterminate form. So L by M should not be undetermined form, and for that reason M should not be equals to 0. L may be 0, then the value will become 0, which is a real number. But when M equals to 0, that will be undefined, that we can't solve. So you can understand that limit of gx which is equals to M should not be equals to 0, then we can divide the formula, right? So let's move to another actually another sorry another result. So again, that particular thing should be same, which is if a limit extending to a fx equals to L and limit extending to a gx equals to M, then the following results are true, right? So these results are says, this result is are says, which is actually limit extending to a f composition z, right? Sometimes it says like f compose g, which is says f compose z, that means actually compose, right? Compose, or you can say composition mapping, composition mapping, right? Composition mapping. So what it actually means, in function you will learn that f compose g at x can be written as f of gx. I mean the the instead of fx we have f of gx, right? So limit at extending to a f compose g at x is equals to limit extending to f of gx. This is the basic property of function, and that can be written as if limit extending to a gx. I mean that limit is actually going inside of the function f, right? So f is actually outside of the limit, then we can take the value, which is actually fm. So in particular, there are two types of functions is given to you. One is limit extending to a log of gx. So basically log gx is a function. So log will be outside of the limit which is there, and we have to take the limit of gx only, right? So that will become definitely, if limit of gx is equals to m, that will become log m, right? Similarly, if e to the power gx is there, then e will be outside of the limit, so that will become e to the power limit extending to a gx, and that will become definitely e to the power m, because limit extending to a gx is nothing but m, so that will become e to the power m. So you can understand that property also, I mean that result also. And this is the last result, which says is limit extending to a fx to the power n, and maybe any kind of real number, that may be positive real number, that may be negative real number, that may be zero. What we have to do, basically put the limit inside the inside this bracket, and that will become limit extending to a fx whole to the power n, right? This is the property, and we know limit extending to fx is nothing but L, so that will become L to the power n for all n belongs to natural number. And this is a very important property, that n should be any natural number, that is n should not be any, you know, n may be real number also, there is no issue, we can take any n from real numbers, right? So there is no issue, but that will change the function, because if n is actually an, suppose if we take n equals to -5, then the function will become limit extending to a fx to the power -5, then that part should not be equals to 0. If that part will become 0, then it will become 1 by 0 to the power 5, I mean 1 by 0, that will be undefined. So it is very necessary that n should be belongs to natural number, or n should be any positive number, right? So you have to remember that thing. So let's move to the next slide, which is actually there are some theories also, right? These are the basic, these are the very important theories. Yeah, so the theory says, if this is actually, so we have already discussed some of the limits when x approaching to some finite number, finite real numbers. It may be x approaching to 2, x approaches to 5, x approaches to 10, x approaches to -5, x approaches to 1000 or something. These are actually finite number. So here in this particular slide, we'll discuss when x approaches to infinity. So I mean, what does it mean actually, x approaches to infinity? X approaches to infinity means, as suppose we have, if we write down limit x approaches to infinity fx, I mean as x approaches to larger and larger and larger value, then where the function fx will be tending to. Suppose if limit extending to infinity, fx will be L. So that means as x approaches to larger and larger and larger value, the function fx will tending to the value which is L, right? If I take an example which is 1 by x, and we have to, if we take limit as x tending to infinity, so you can understand that when we increase the value of x, right? Suppose if x equals to 100, then 1 by x will become 1 by 100. If we'll take x equals to 500, then 1 by x will become 1 by 500. As we move to the larger value and larger value of x, then we can see that 1 by x is actually trying to converge, or trying to tending towards the value which is 0, right? So the graph would be similar like that. So as we increase the value of x, you can see the graph will trying to touch the x-axis. I mean that 1 by x will become 0. So limit extending to infinity, 1 by x will become 0. So what this particular theory says is, if x tending to infinity, I mean x is a very large amount of value, and x is actually trying to become very large and large and large, then x to the power positive thing. I mean, if I write down x to the power a, where a is greater than 0, this is similar as x to the power positive sign. So x to the power positive sign will also tending to infinity. So what are the examples? Suppose x tending to infinity, then x to the power 2. So 2 is actually a positive sign, right? I mean a positive quantity. Then x to the power 2 will be tending towards infinity. Similarly, x to the power 5 will also tending towards infinity, because 5 is also a positive number. Similarly, x to the power 3 by 2 will always tending to infinity. I mean 3 by 2 is also a positive quantity, right? So can you tell me where the root x will become? Since root x is nothing but x to the power half, and half is actually also a positive quantity, then root x will also tending towards infinity. So this is actually the first theory. And the second theory says if x tending to infinity, so this is fixed, right? X tending to infinity and x tending to infinity. Then x to the power negative, I mean if x to the power a, where a is less than 0, or you can say x to the power minus a, where a is greater than 0, x to the power negative things will be tending towards 0, right? Will be tending towards 0. Or you can think that x to the power negative thing can be written as x to the power minus a, where a is greater than 0, and that can be written as 1 by x to the power a. So when x tending to infinity, x to the power a will become infinity, and 1 by infinity is nothing but tending towards 0, right? So that is why x to the power negative will tending towards 0. So what are the examples? So as x tending to infinity, then x to the power minus 2, I mean x to the power negative symbol, that will become 0. Similarly, x to the power minus 5 will 0, x to the power minus 3 by 2, which also negative sign, this is also 0, and that part will also 0, right? So you can understand what is the theory, what the theory says, right? Yeah. So let's move to the another theory, which is for limit extending to infinity. So we have two functions, and those functions are actually polynomial expression, right? You know, right? What is polynomial expression? A polynomial expression is almost looking like a naught plus a1x plus a2x square plus dot 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 plus a n x to the power n, right? This type of polynomial expression. And this polynomial expression is very important. I have already discussed with you, right? So for limiting value as extending to infinity fx by gx, where fx is a polynomial expression and gx is a polynomial expression, then when this type of, so how we can find out these types of limit, right? So basically, in order to find out these types of limit, what are the methods? The method is actually we have to divide on the numerator and denominator. We have to divide on the numerator and denominator by the highest power, or you can say by the highest degree of variable. So basically, when we see that limit of extending to infinity fx by gx type, question is given to you, and you can see that fx and gx are the polynomials. Then you have to try to find out what are the highest degree of these particular expressions, right? And you have to divide the numerator and denominator by the highest degree variable. If we have cubic equation as fx and we have another cubic equation as gx, then the highest degree variable is x cube. So we have to divide the numerator and the denominator by x cube, right? So let's move to some questions so that you can understand, right? Very easily. So basically, we have limit extending to infinity, and the function is given to you is 3x square minus 5x plus 6 upon x square plus 7x minus 6. So here this function is called as fx, I mean the first function, and this function is nothing but gx, right? So fx and gx are polynomial, so there is no issue, right? Polynomial. So can you tell me what is the highest degree of fx? So I mean the degree of fx is nothing but degree of fx is equals to 2, because you can see the highest power of x is 2. Similarly, the degree of gx is nothing but 2, because here you can see the highest power of x is 2. So the method says we have to divide the numerator and the denominator by the highest degree of variable. So you can understand we have to divide by x square on the numerator and the denominator, because as we put x tending to infinity on the numerator and denominator, that will become infinite by infinite form. So we can't solve infinite by infinite as in a straightforward manner, because this is actually an undeterminate form, right? So let divide the numerator and denominator by x square. So that will become limit x tending to infinity. The numerator will become 3x square minus 5x plus 6 upon x square, and the denominator will become x square plus 7x minus 6 upon x square. So since we can write this equation as limit x tending to infinity, that will become 3x square by x square, right? We can write down that as 3x square by x square minus 5x upon x square, right, plus 6 upon x square, and the denominator can be written as x square upon x square plus 7x upon x square minus 6 upon x square, right? So that will be similar as limit x tending to infinity. X square will be cancelled out. We have 3 minus x, and x square will be cancelled out, and we have 5 upon x, because when we cancelled x by x square, that will become 1 by x. So, and that part will be 6 upon x square, and the denominator will be 1 plus 7 by x minus 6 upon x square. So you can see as x tending to infinity, sorry, as x tending to infinity, 5 upon x will tend to 0. Why? Because 5 upon x will tending to 5 upon infinity, because x tending to infinity, and something finite upon infinity will tending to 0, because infinity is a very large quantity, and that is actually sitting on the denominator, right? Sitting in the denominator, and that will trying to make that particular expression as 0, right? So 5 by x will tending to 0. Similarly, 6 by x square will also tending to be 0. 7 by x will also tending to 0, and 6 by x square will also tending to 0. Why? Because we have another method which is actually limit x tending to infinity. We can actually change the limit on the both side as the as the right, the result name is actually the division formula, right? We can apply the division formula. Let us apply the division formula so that you can understand what am I trying to say, right? What am I trying to say? Just wait a second, please. Just wait a second. I will trying to solve all these things. Yeah. So let us apply the division formula. The division formula says we can change the limit as limit extending to infinity. The numerator will become 3 minus 5 upon x plus 6 upon x square, as limit x extending to, suppose a, fx by gx will be limit extending to fx upon limit extending to a gx. So that will become limit extending to infinity 3 minus 5 by x plus 6 by x square, and that will become limit extending to infinity 1 plus 7 upon x 1 plus sorry 1 plus 7 upon x minus 6 upon x square. Then we know that if sum or subtraction of functions is given is there, then we can change the limits also, right? So that will become limit x tending to infinity 3 minus limit x tending to infinity 5 upon x and plus limit x tending to infinity 6 upon x square, right? And the denominator will become limit x tending to infinity 1 please, plus limit x tending to infinity 7 upon x minus limit x tending to infinity 6 upon x square, right? And we have another formula which is limit, suppose x tending to a, k f x is there, so that can be written as k times limit extending to a fx, right? So we can actually put that constant term outside of the limit, right? So similarly we know, right, constant term limit will be same as that constant term, so 3 minus that can be written as 5 times limit extending to infinity 1 upon x, right, plus 6 times limit extending to infinity 1 upon x square, and the denominator will become, that will become 1 1 plus 7 times limit extending to infinity 1 upon x minus 6 times limit extending to infinity 1 upon x square, right? So here you can see that 1 upon x can be written as x to the power minus 1, and minus 1 is a negative symbol, and as x tends to infinity, x to the power negative things will tending to 0, right, as the previous result. Similarly 1 upon x square can be written as x to the power minus 2, and minus 2 is a negative quantity, so x to the power negative quantity will tending to 0 as x tending to infinity. Similar case will happen for that result also and that result also. So 5 times 0 will become 0, 6 times 0 will become 0, 7 times 0 will become 0, and 6 times 0 will become 0. So that become 3 minus 0 plus 0 upon 1 plus 0 upon 0 minus 0. So that will become 3 upon 1, which is equals to 3. So the value of the given function, which is actually I erased it, that is equals to 3 only, right? So you can understand. So what we did actually, we did basically trying to find out that whether those polynomials, right, where fx by gx is given to you, fx and gx are actually a polynomial equation or not. If it is polynomial equation, if those are polynomial equations, then we have to try to find out what will be the highest degree of those polynomials, and after that we have to divide these polynomials by that particular degree of variables, and after that we have to use the previous results and we can solve that particular problem, right? So let's move to another question. This is a very interesting question. Here it says that limit extending to infinity 2x plus 1 to the power 40 times 4x minus 1 to the power 5, and the denominator is 2x plus 3 to the power 45. So as we put x tending to infinity, what we have to do at first, like we have to substitute the value of x. You can see that total part will tending to infinity because those are actually positive quantity. Similarly, the denominator part will also tending to infinity, right? So that will become infinite by infinite form, I mean the undeterminate form. So we can't solve this particular thing by the substitution method. But here you can see, if we expand this particular term, that will become a polynomial expression of degree 40, right? Or you can say that there will be a polynomial which has x to the power 40 as the highest degree when you expand 2x plus 1 to the power 40, and when we expand 4x minus 1 to the power 5, we have degree 5, right, for that particular equation. Similarly, when we expand this particular expression, we'll get a part of x to the power 45, right? So these are actually polynomials. And so 2x plus 1 to the power 40 is a polynomial. 4x minus 1 is also a polynomial, right? But here you can see that degree of this particular polynomial is 40 and degree of this particular polynomial is 5. When we multiply them, then the degree of that total polynomial will be 45. Similarly, degree of that particular polynomial will also 45 because 45 is there. And if we just multiply this after expanding, we will get degree of terms 45, right? That means there is a term related to x to the power 45 as the highest degree of variable. So there is a term x to the power 45. So we have to divide. So we have to divide the functions by x to the power 45, right? The functions by x to the power 45. So that will become limit x tending to infinity, and the numerator will become 2x plus 1 to the power 40 times 4x minus 1 to the power 5 upon x to the power 45, and the denominator will become 2x plus 3 to the power 45 upon x to the power 5, as that part has degree 45 and that part has degree 45, right? So now we can we can write that particular polynomial as, we can write down that particular polynomial as 2x plus 1 to the power 40 upon x to the power 40, right? X to the power 40 times 4x minus 1 to the power 5 upon x to the power 5, right? I can do x to the power 45 as x to the power 40 times x to the power 5, and we have to take x to the power 40 with 2x plus 1 to the power 40 and x to the power 5 with 4x minus 1 to the power 5, and the denominator will become 2x plus 3 to the power 45 upon x to the power 45, right? X to the power 45. Yeah. So here you can see, suppose if we have x to the power n, and if we have suppose y to the power n, that can be written as x upon y to the power whole to the power n, right? Similarly here 2x plus 1 to the power 40 is there, and x to the power 40 is there. Since 40 and 40 are same, so we can write down that particular function as 2x plus 1 upon x whole to the power 40, and that particular function as 4x minus 1 upon x to the power 5, and that denominator part can be written as 2x plus 3 upon x to the power 45, right? So let's write down on the left side. So here we can change the limit, right? We can change the limit. So if we change the limit, I'm not doing these things because these are actually trivial things. What we have to do is basically we have to change the limit, then limit of that part upon limit of that part, right? That will happen. And after that we have to separate the limit as fx and gx. I mean, multiplication of these two functions are there. So we can write down the numerator as limit x tending to infinity 2x plus 1 upon x to the power 40 times limit x tending to infinity 4x minus 1 upon x to the power 5, and the denominator will become limit x tending to infinity 2x plus 3 upon x to the power 45, right? So let's erase some parts so that we have more spaces, and then we can solve by by taking this thing. Just wait a second, please. Let me erase those parts. Yeah. Okay. So what we have is basically we have this particular expression. So here you can see 2x plus 1 upon x can be written as 2x upon x plus 1 upon x, right? That can be written as limit x tending to infinity 2x upon x plus 1 upon x, right? So that can be also written as 2 plus 1 upon x, and which is to the power 40 times limit extending to infinity, that can be written as 4 minus 1 upon x, because those x will be cancelled out, right? This x will be cancelled out, so that will become 4 minus 1 upon x to the power 5. And the denominator part will become limit extends to infinity 2 plus 3 upon x to the power 45, right? So you have also a formula, you have also a theory, which is actually, if limit extending to a fx to the power n is there, that can be written as limit extending to a fx whole part to the power n. Similarly, here you can see the function is actually 2 plus 1 upon x to the power 40, and limit is outside of the function. So that can be written as limit extends to infinity 2 plus 1 upon x, that part to the power 40, right? Times, that can also be written as limits extends to infinity 4 minus 1 upon x, that part to the power 5, right? That part to the power 5. Let me erase these parts. Yeah. And the denominator will become limit extending to infinity 2 plus 3 upon x, that part to the power 45, right? That part to the power 45, right? Yeah. So let's erase that part. Just wait a second. So here you can see, since two functions are there, so we can also change the limits, like limit fx plus limit gx, I mean limit 2 plus limit 1 by x, and that will become 2 plus limit 1 by x. So 1 by x will tend to 0, so that will become 2 plus 0, and that to the power 40. So that will also become 4 minus 0, right? 4 minus 0, that part to the power 5, and the denominator will become 2 plus 0, right? 2 plus 3 times 0, I mean 0, right? Because 3 by x will tending to 0 and 2 will be tending to 2, because limit of any constant function will become that particular function. So that will become 2 plus 0 to the power 45, right? So what will you have? 2 to the power 40, right? We'll have 2 to the power 40, and we will also have 4 to the power 5, and on the denominator we have 2 to the power 45. So if we cut that two part, then we'll have 2 to the power 5 here, right? So 4 to the power 5 can be written as 2 times 2 to the power 5 upon 2 to the power 5, right? And that can be written as 2 to the power 5. Just wait a second, please. That can be written as 2 times 2, right? So that will become 2 to the power 5. That will become 2 to the power 5 times 2 to the power 5, right? You have already understand what am I trying to say, right? So can you please tell me what will be the value of this particular thing? So that will become 4 times, wait a second please, 4, yeah, that is true, right? So you can calculate that part, and that will become 2 to the power 5 times 2 to the power 5, and the denominator will become 2 to the power 5, and 2 to the power 5 and 2 to the power 5 will be cancelled out, and we have 2 to the power 5, which is nothing but equals to 32, right? Because 2 to the power 2 will be 4 times 4 will be 16 times 2. I mean 2 to the power 5 can be written as 2 times 2 times 2 times 2 times 2. I mean 5 times product, right? So that will become 4 times 2 times 8. 8 times 2 will be 16, and 16 times 2 will be 32. So the given function has value 32, right? So you can understand what I actually did here, right? Yeah. So this is all about for the lecture, right? So thank you for joining this lecture. We'll meet tomorrow. Thank you for joining this lecture. Thank you so much.